Hello everybody. Today we are going to study Fourier series. As we know that Fourier series is very helpful in the study of conduction of heat, mechanics, electrostatics and many such fields. Fourier series first introduced in 1807 by Fourier. Fourier series is an infinite series representation of periodic function in terms of the trigonometric sine and cosines. Fourier series is a powerful tool to solve the ordinary and partial differential equations. So as we know, Fourier series is the series representation of periodic function. First of all, we will see what is periodic function. Periodic function if f of x is a function defined in some interval and t is a positive quantity such that f of x plus t equals to f of x, then we say that f is a periodic function. And if t is such smallest quantity, that means t greater than 0 is smallest such that f of x plus t equals to f of x, then this t is known as period of function f. If t is the period of a periodic function f, then we have this property f of x plus nt equals to f of x for any integer here. Okay. So with this much information about periodic function, now we are going to define Fourier series. If f of x is a function which satisfies following conditions. Number one, f of x is a periodic function. With some period, say 2l. Second thing, this f of x has only finite discontinuities. Third property, f of x and its integral both are finite. Finite as well as single value, obviously. And finally, this f of x has finite maxima and minima values. If a function f of x satisfies these four conditions are known as Dirichlet's conditions. If any function satisfies these Dirichlet conditions, then that can be represented as a Fourier series. Now we will see what is the Fourier series representation of function f, which is periodic with period 2l defined on some interval c to c plus l. F of x is periodic with period 2l defined on the interval c to c plus 2l. Then its Fourier representation is given by f of x equals to a0 by 2 plus summation an cos n by x upon L, summation varies from 1 to infinity, plus summation bn into sine n pi x upon L. This summation also varies from 1 to infinity. This equation 1 is known as Fourier representation of f of x, where this a0, an and bn are obtained by this formula. a0 equals to 1 upon L integral c to c plus 2L f of x dx. An is 1 upon L integral c to c plus 2L f of x into cos n by x upon L into dx. And Bn is 1 upon L integral c to c plus 2L f of x sin n by x upon L into dx. So let this is equation 2, this one is 3 and this one is 4. This equation 2, 3 and 4 are known as Euler's equations. These are known as Euler's equations. Now we'll see different cases, and for that cases how this Fourier series and these coefficients are determined. First of all, we'll see the case where c is 0. What happens if c is 0? If c equals to 0, the interval of definition will be 0 to 2n. And Fourier's representation will be given by the equation 1. And this a0, an and bn now are obtained in this way. These values are given by 1 upon L integral 0 to 2L f of x dx. An is 1 upon L integral 0 to 2L f of x cos of n by x upon L into dx. And Bn is 1 upon L integral 0 to 2L f of x sin of n by x upon L into dx. So this is a case where c is 0. Now when c is 0, the interval of definition is 0 to 2L, and accordingly these coefficients a0, an and bn are obtained in this way. Now we will see the case 2, where c is minus pi and L is pi. This is case number 2. That means we are taking period equals to 2 pi and interval is minus pi to plus pi. So in this case, the Fourier series expansion now will be like this. F of x equals to a0 by 2 plus summation n varies from 1 to infinity an cos n pi x upon L. Here L is pi again, therefore this is cos nx plus summation bn sin nx, n varies from 1 to infinity. Okay. So give some number to this equation. Take 8. And these coefficients a0, an and bn are given. a0 equals to 1 upon L. L here is pi, so it is 1 upon pi. Integral c to c plus 2L. So c is minus pi, 2L is 2 pi, so integral is minus pi to pi into f of x dx. Okay. And an is given by 1 upon pi integral minus pi to plus pi f of x into cos nx now into dx. And bn is given by 1 upon pi integral minus pi to plus pi f of x into sin nx dx. So this is the case 2 where c is minus pi and we have taken period equals to 2 pi. So the definition of interval is minus pi to plus pi. Third case, where we will take c equals to 0 and L equals to pi. Case number 3, where we take c equals to 0 and L equals to pi. What happens here? C equals to 0 and L equals to pi. If I take this value, then the interval of definition for this function will be 0 to 2 pi. And accordingly, this Fourier series will take the form f of x equals to a0 by 2 plus summation n varies from 1 to infinity an cos nx plus summation bn into sin nx. Okay, and the coefficients are given by a0 equals to 1 upon pi integral 0 to 2 pi. Now c to c plus 12 means 0 to 2 pi f of x dx. An is given by 1 upon pi integral 0 to 2 pi f of x into cos nx dx, and bn is given by 1 upon pi integral 0 to pi f of x into sin nx dx. So this is the case 3. Now case 4, where we will take c equals to minus L and period equals to L as it is. Okay, so this case we will consider c is minus L and period is 2L. What happens if I consider like this? The Fourier series is again given by equation 1, no doubt, because period is 2L. Only what changes here to find a0, an and bn. a0 now is equal to 1 upon L integral minus L to plus L, c to c plus 12 means minus L to 2L f of x dx. An equals to 1 upon L integral minus L to plus L f of x cos n pi x upon L into dx, and bn is given by 1 upon L minus L to plus L f of x into sin of n pi x upon L into dx. So this is case number 4. So these are the different 4 cases, and in these cases the representation of function f of x as Fourier series and how to determine a0, an and bn.